Welcome back to G Fun Facts Online. Today we are discarding the preamble to dive straight into one of the most critical developments in modern immunology and pandemic preparedness. We are looking at the threat of H5N1 avian influenza as it stands in February 2026, and specifically why the future of our survival may not depend on a shot in the arm, but on a spray in the nose. To understand the gravity of this moment, we have to look at the biological reality we face. For decades, H5N1 was a distant threat, a virus that decimated poultry but struggled to unlock human cells. That has changed. Following the outbreaks in dairy cattle in 2024 and 2025, the virus has undergone what is effectively a massive, unintended gain-of-function experiment in nature. Cows possess both avian-like and human-like receptors in their respiratory tracts, allowing the virus to mix, reassort, and learn. As of early 2026, the clade 2.3.4.4b variant has demonstrated an unsettling capacity to replicate in the mammalian upper respiratory tract. We have seen over 70 human cases in the United States alone since 2022. While human-to-human transmission remains inefficient, the biological barriers are eroding. This brings us to the core problem of our current defense strategy. Traditional pandemic planning is reactive. We wait for a strain to emerge, we manufacture an injectable vaccine, and we deliver it intramuscularly. However, the last few years have highlighted a fatal flaw in this logic. Intramuscular vaccines are excellent at preventing severe pneumonia and death because they stimulate systemic IgG antibodies in the blood. But they are poor at preventing the initial infection in the nose and throat. In a respiratory pandemic, a vaccine that prevents death but allows infection is a leaky dam. It slows the flood, but it does not stop the transmission. This is where the concept of the mucosal shield comes into play. If we can fortify the nasal gate, the very portal of viral entry, we can theoretically achieve sterilizing immunity. This is protection that prevents the virus from ever establishing a foothold, thereby cutting the chain of transmission entirely. To understand how this works, we need to analyze the anatomy of the battlefield. The human respiratory tract is not a uniform tube. It is a complex system with distinct immunological provinces. Influenza viruses gain entry by binding to sialic acid residues on the surface of epithelial cells. Avian influenza prefers alpha-2, 3-linked sialic acids, which in humans are found deep in the lungs. This is why bird flu historically caused severe pneumonia but did not spread easily through coughing. Human influenza, however, prefers alpha-2, 6-linked sialic acids, which are abundant in the nose and throat. The danger of the current H5N1 evolution is that the virus is becoming better at binding to these alpha-2, 6 receptors, particularly in the inflamed tissues of the nasal passages. Once the virus can replicate in the nasopharynx, every sneeze becomes a biological weapon. This is why we need to activate the nasopharynx-associated lymphoid tissue, or NALT. Think of the NALT as the command center for the local immune system in your head. When you get a standard flu shot in the arm, it bypasses this command center entirely. It stimulates lymph nodes in the armpit to produce antibodies that circulate in the blood. These antibodies are like a heavy cavalry stationed at a military base far from the border. They can rush in to save the vital organs once the invasion has begun, but they are not stationed at the wall. The goal of intranasal vaccination is to deploy a different kind of defender, specifically secretory IgA and tissue-resident memory T cells. Let us break down secretory IgA. This is the most abundant antibody in the body, yet it is often ignored in standard vaccine trials. Structurally, it is unique. Unlike IgG, which is Y-shaped, secretory IgA is a dimer, meaning it looks like two Ys joined tail to tail. This gives it 4 binding sites instead of 2, significantly increasing its ability to grab onto viral particles. Furthermore, as it is transported to the surface of the nose, it picks up a secretory component that stabilizes it against the harsh environment of mucus. Its primary function is immune exclusion. It binds to the virus and clumps it together in the mucus, preventing it from ever touching the cell surface. The trapped virus is then swept away by tiny hairs called cilia and swallowed. While antibodies prevent entry, we also have the tissue-resident memory T cells, or TRM cells. These are the sleeper agents of the immune system. Unlike systemic T cells that patrol the blood, TRM cells park themselves permanently in the nasal tissue. They do not patrol, they wait. Research published in late 2025 has shown that these cells are cross-reactive. Even if the H5N1 virus mutates, these T cells recognize internal viral proteins that change less frequently. An intranasal vaccine establishes these sleeper cells directly at the site of potential infection, allowing for a reaction time measured in hours rather than days. We must contrast this with the failure of the needle. In ferret studies conducted throughout 2024 and 2025, intramuscular H5N1 vaccines successfully prevented death. However, when those vaccinated ferrets were exposed to the virus, they still became infected in the nose and shed the virus for several days. Applied to a human pandemic, This means a vaccinated nurse could survive the infection but still carry it home to her unvaccinated family. This silent spreader phenomenon makes containment nearly impossible with injectable vaccines alone. Systemic antibodies take time to leak from the blood into the nose. In a race against a fast-replicating virus, this lag time is critical. The virus can replicate to high levels before the systemic defense arrives. This brings us to the breakthroughs of the last 12 months. We are currently witnessing a renaissance in mucosal vaccinology. In January 2026, researchers at Washington University School of Medicine in St. Louis published results that have reshaped the field, led by DRs. Jaco Boone and Michael Diamond, the team developed a nasal vaccine using an adenoviral vector. Unlike previous nasal flu vaccines like FluMist, which use live attenuated influenza, this uses a harmless common cold virus engineered to carry H5 proteins. In animal models, this vaccine provided near-complete sterilizing immunity. When challenged with lethal doses of H5N1, the vaccinated animals showed no detectable virus in the nose or lungs. The shield held. Crucially, they engineered the vector to bypass pre-existing immunity, a historic stumbling block for viral vectors. Simultaneously, the University of Maryland School of Medicine has been developing a protein nanoparticle vaccine, the NanoVax. Their Phase 1 clinical trial results, released in late 2025, showed that this vaccine acts as a super primer. When participants received a nasal prime followed by a standard shot, or vice versa, the immune response was synergistic. It also demonstrated epitope broadening, meaning it triggered immunity not just against the specific H5 strain in the vaccine, but against divergent strains. This is the holy grail of flu research, a vaccine that protects against the virus of today and the mutated virus of tomorrow. Not to be outdone, Duke University researchers have adapted mRNA technology for the nose. The challenge with mRNA has always been getting it through the mucus. Duke developed a lipid nanoparticle formulation that can penetrate the mucus layer and enter the nasal epithelial cells directly. Their dual antigen approach encodes both hemagglutinin and neuraminidase, preventing the virus from entering cells and preventing it from leaving if it does manage to replicate. Now, let us look at the mechanism of action in detail. When the WashU adenoviral vaccine is sprayed into the nostril, it infects the epithelial cells of the nasal turbinates. These cells begin to produce the H5 hemagglutinin spike protein. This triggers a local alarm. The NALT detects this foreign protein and creates a local storm of cytokines, recruiting B cells and T cells specifically to the nose. These B cells differentiate into plasma cells that reside in the nasal lining and pump out dimeric IgA. They are programmed with a homing signal that keeps them in the respiratory tract. When the actual H5N1 virus is inhaled later, it encounters a sticky mucus layer filled with these antibodies. The SIgA binds to the viral spikes, cross-linking them into large aggregates. The virus is physically unable to reach the receptor. It is the biological equivalent of putting glue in a lock. But if nasal vaccines are so superior, why haven't we used them for everything? The answer lies in the difficulty of delivery and the history of safety. The nose is designed to keep things out. It is a filter. Getting a vaccine past the mucus without causing irritation is difficult. There is also the shadow of Bell's palsy. In the early 2000s, a nasal flu vaccine licensed in Switzerland used a bacterial toxin as an adjuvant to boost effectiveness. It worked, but it caused inflammation that compressed the facial nerve, leading to paralysis in some patients. This stalled research for a decade. However, the new generation of vaccines uses safer adjuvants. The NanoVax uses a proprietary adjuvant that stimulates toll-like receptors without damaging nerve tissue. The WashU adenovirus acts as its own adjuvant because the virus capsid naturally stimulates the immune system. Novavax has also successfully tested their Matrix M adjuvant, derived from saponin tree bark, in nasal formulations. Another historic critique is that mucosal immunity is short-lived. However, 2026 data challenges this. The inclusion of new adjuvants appears to stimulate long-lived plasma cells in the bone marrow that continue to supply IgA to the mucosa for extended periods. Furthermore, the establishment of resident memory T cells provides a backup defense that lasts for years. We also need to consider the One Health application. The H5N1 crisis is fundamentally an animal health crisis. The spread of the virus in dairy cattle and poultry is the engine driving the pandemic risk. Injecting 100,000 chickens individually is logistically impossible. However, mucosal vaccines can be administered via aerosol, essentially spraying the flock. The same adenoviral vector technology proving effective in humans is being adapted for veterinary use. A study in late 2025 demonstrated that aerosol vaccination of poultry induced herd immunity, stopping the spread of highly pathogenic avian influenza in a flock. By building a mucosal shield in the animal reservoir, we reduce the viral load in the environment, lowering the risk of spillover to humans. As of February 2026, the regulatory landscape is shifting. The FDA and EMA have established new correlates of protection for mucosal vaccines. Previously, approval required showing high levels of serum antibodies. Now, regulators are accepting mucosal IgA titers and T-cell assays as valid endpoints for efficacy. The UM-SOM Nanovax is currently in Phase 2 trials, and the WashU candidate is being fast-tracked for Phase 1 and 2 combined trials, funded by BARDA. The timeline for a deployable commercial product is estimated at 12 to 18 months, but in an emergency use scenario, this could be accelerated. In conclusion, the emergence of H5N1 as a mammalian pathogen has forced the scientific community to confront the limitations of 20th century vaccinology. The shot in the arm was a triumph of its time, effective against systemic diseases like polio and measles. But for a rapidly evolving mucosally transmitted virus like influenza A, it is an incomplete solution. The research of 2025 and 2026 has provided the proof of concept for a new era. We now possess the technology to build a shield at the gate. These nasal vaccines offer the promise of interruption. They do not just mitigate the damage, they stop the invasion. There are also global implications to consider. If candidates like the WashU vaccine reach global distribution, the logistics of pandemic response change distinctively. A nasal spray can be self-administered. It eliminates the bottleneck of needing medical personnel to give injections. In a pandemic, millions of doses could be mailed to households. Furthermore, many of these new formulations are stable at refrigerator temperatures, avoiding the ultra-cold chain requirements of early mRNA vaccines. This is crucial for distribution in the global south, where H5N1 is endemic. As H5N1 continues to probe the defenses of the human population, the race is no longer just about the speed of manufacturing, it is about the route of administration. The needle may save the patient, but the nasal spray will save the population. The mucosal shield is no longer a theoretical ideal, it is our most viable strategy for a pandemic-free future. Thank you for listening to this deep dive on G Fun Facts Online.